Alright, now it's time to talk about our third element of sound, and that is phase. Now when we start talking about phase, this is where it gets to be a little complicated, but it's not once you get the fundamental concepts down. What's going on here is phase is mostly about time relationships between two or more sounds. And when you're looking at it, phase is measured in degrees. All right, and the reason why it's measured in degrees is because what we're looking at down here is one cycle of a wave. We discussed this before. One cycle of a wave is going from zero pressure to maximum pressure, which is the compression, past zero pressure to maximum minimum pressure, which is the rarefaction, and back up to zero pressure. That's one complete cycle. Well, if you look at this, this is actually a circle that's been sort of cut in half down the middle and then flipped over or flipped around. So because of this, because it's just one big circle that's been flipped around on itself, it's measured in degrees. And each cycle has 360 degrees to it, just like a circle has 360 degrees. So when we're measuring at what point you are in this cycle of any given wave, it is measured in degrees. Alright, so how does this work? Why do you do it? Alright, the phase of any point on a wave is its degree of progression in the cycle. It's basically, the degree is almost a measurement in time. Where are we in time on that sound wave? Because sound travels through time, it moves forward through time. And so when we're measuring the degree, we're saying where are we in time on that cycle. Phase is measured in degrees, with 360 degrees being one complete cycle. The beginning is 0 degrees, the peak will be 90 degrees, and so on. Alright, so phase is measured in degrees. So if I were to say what is phase measured in, I will say it's measured in degrees. Alright, so what does this mean? Well, up to now, we've been looking at just one sound wave, one individual sound wave. Well, the real world does not work that way. The real world, there are countless sounds interacting with one another. And multiple sound waves affect other sound waves. If you've ever been to the beach and you see, you can do it yourself in the bathtub or in a sink, put a drop of water and make a ripple happen. Then cause a second ripple. When those waves hit each other, things happen. The waves change. Well, what happens is you have what is called a phase shift. All right, a phase shift. So what this means is that if one wave interacts with another wave, the peaks and the troughs will affect one another. And the peak of one will actually pull down on the other. It's like a tug of war when those two ripples hit. And so again, this is an experiment you can do in a sink, fill a sink with water, or get a basin of water in a bathtub, and make ripples on one side of the tub, and then make ripples make a ripple of water on the other side of the tub. And when you see those two waves come at each other, whichever is the largest wave will reduce in size when they meet. All right, because two sine waves or two waves meeting each other will either cancel each other out if they're exactly the same, or they'll reduce the larger and amplify the weaker to create a brand new wave. But phase shift but if there is a phase shift of 180 degrees, remember 180 is half of a circle, 360 divided by half. If you have two waves that are of identical size, and they meet, you get what's called a phase shift between the two identical waves, and the peak of one wave and the trough of the other will cancel each other out. So this wave will essentially turn into this, just a straight line, nothing. So that's called phase cancellation. Now, rarely in nature do you get a complete phase cancellation of frequencies, but it does happen. And this can be a problem in situations where you're recording or if you're in a live environment. If you've ever been to a concert in a bar or some place that's not really doesn't really have great acoustics, and you think that the band sounds really flat or they just don't sound good or as good as you normally have them, there's a possibility that whoever is running sound for them is not taking phase shifting into account, because there will be a slight reverb or a possible echo in some environments that are not acoustically meant for concerts, and some phase shifting will happen, and some of those frequencies will cancel each other out, because you get the one frequency going out, it will hit a wall and bounce back, and those frequencies will hit the other frequencies coming back in, and then you can get phase cancellation happening of some frequencies, which is why they can sound flat. You're not hearing the full sound because their own audio is canceling itself out, bouncing off the walls. Sorry. Another term for this is phase cancellation or interference. Alright, what happens if sound is partially out of phase? Like 90 degrees versus completely out of phase. This is where we start to see what we are hearing when sounds are partially out of phase. Alright, this is where we start getting the sounds that we hear in the quote-unquote normal world. As I said before, we never hear a pure sound wave. Almost never hear a pure sound in the real world. Well, it's always going to be influenced by other sounds in the place. What we do hear are complex waves. Alright? And we will be looking at what are the fundamentals of these complex waves. Well, a sine wave, as we've been looking at, is a very simple, pure tone. And it can pretty much only be created electronically. Complex waves have many frequencies with each other at varying levels, meaning varying amplitudes. Out of those complex waves, there are always fundamentals, which are the lowest frequency in a complex wave is the lowest pitch of the sound. There is no such thing as a pitch below the fundamental. Alright? So all harmonics, essentially what we're talking about, all complex sound waves have a fundamental frequency that must be paid attention to understand what this complex wave is. Harmonics. Alright, you've all heard people harmonizing. You've heard, guitars and notes and things like that. You're probably hearing my clock chime in the background right now. Harmonics are tones whose frequencies are integral multiples, right here, of the fundamental frequency of the wave. What this means is that if something is a harmonic, it is a multiple. It means it can be multiplied by the fundamental frequency. The example in the notes here is that if you have a fundamental frequency of 440 hertz, so that's your fundamental, that's the lowest frequency in that sound, that harmonic. The harmonics of that will be 880, 1320, and so on. In other words, the second harmonic is 440 times 2. That's the second harmonic, which equals 880. The third harmonic will be 440 times 3, which equals 1320. The fourth harmonic will be 440 times 4. Fifth harmonic would be 440 times 5. So it's just very simple mathematics. You multiply it by whatever level harmonic it is, and you will know what the harmonic of the fundamental is. Harmonics are numbered in order of increasing frequency. The first harmonic is always the fundamental frequency. The second is twice the fundamental, and so on. So it's very simple math. If someone says, what's the harmonic of this complex wave? First thing you want to ask is, what is my fundamental frequency? And then from the fundamental, all the other harmonics can easily be determined just by simple multiplication. All right. So what makes complex waves complex? All right. Well, complex waves, basically, as we discussed, are multiple frequencies. I put HZ in there just for shorts for frequencies. But complex waves are multiple frequencies. But there's always just one fundamental. Now, that being said, in the real world, you're not always going to have all harmonics happening. There will be overtones, and also sometimes called upper partials. There will always be overtones and upper partials happening on any frequency. Harmonics are always multiples of the fundamental. Overtones and upper partials are everything else. All right? They are all the frequencies that come between the harmonics. And we'll get back to that more in a second. But looking back at how a harmonic works. Here is our fundamental. This is why a harmonic works. This will be the second harmonic of the fundamental frequency. See how it fits twice within the same span of that frequency. And then if we were to do the third harmonic, it would be more complicated than I can draw, but something like that. So they fit within, they all line up within that fundamental frequency. That's why they are in harmony with one another. All right, it all fits in with the same cycle, the same wavelength. That's why they are in harmony with one another. When you hear things are in harmony with one another, that's why they're in harmony. You're hearing those different frequencies come together, but they fit. So what's really happening with our harmonies? Well, or any complex wave. If you look at this, this is our fundamental frequency. This is, for this example, this is our third harmonic of the fundamental. The pull, or the push, and the pull of the peaks and the troughs on both these waves actually give us a new shape to the sine wave. It gives a new peak to it, new shape, and this is what we're hearing. If you measure this, you would be able to measure this on an oscilloscope. This bottom one is what we are actually hearing. So even though there are multiple frequencies playing, the multiple frequencies come together to create almost a brand new frequency that didn't exist before that we are hearing. And this is how harmonics work. It's how we get these interesting sounds. Just another going back now to looking at harmonics and overtones and upper partials. In complex wave, if we have a fundamental frequency of 50 hertz, the overtones are going to be anywhere from 51 hertz to 99 hertz. Those are upper partials, also called the upper partials. The second harmonic, if it will be 100 hertz, the overtones would be 101 to 149. Third harmonic would be 150, so on and so forth. So there's always going to be a lot more overtones and upper partials than there are harmonics of a fundamental. Getting back to how these work, how these fundamentals and things and harmonics work with one another. Just give you another explanation of how they work. Here is your fundamental. Here is the second harmonic of the fundamental. And this is how they line up. Again, showing how a brand new wave comes to be by combining. You can see here we actually have a whole new set of peaks and troughs to create a new sound within this space. This is how they all line up. Now, what does this mean in the real world? This is why an A note on a piano sounds different than an A note on a guitar, or an A note on a saxophone, or an A note on a vocalist, a person singing, because there are tons and tons and tons of different harmonic frequencies in there making up that A note based off of the different instruments, and they all also have different overtones and upper partials based off of the materials that the instruments are made out of. Guitar is, the shape of it, the kind of wood, the kind of strings that are used, how is it plucked, is it strung, is it strum, do you blow through it, or how any number of different ways that those notes are created. The fundamental frequency will be the same, but the harmonics and the overtones and upper partials will always be different. This is referred to as the timbre of the instrument, is the quality of the tone. This is why one instrument will always sound different than another. That's it. Thank you.